steadily increasing. So one consequence is that the roads are being highly frequented during the next years, and there are a few nice interesting statistics, for instance from the federal office, the Federal German Office of Statistics, saying that every German spends about 70 hours each year inside traffic jams. So the economy loses about, I think, 90 billion euros each year. And there's a really nice forecast in Salzburg saying that in the year of 2015, travel times only in Salzburg are increasing by 15 minutes per trip. So I think these facts really make it necessary to develop some innovative solutions. And one approach we were following is using road or deriving road data from single users, which are moving inside the traffic networks as an active source of information. So not just as a passive sensor, also as an active part of the generating traffic data. So the objective would be to form a community to detect the traffic conditions and to derive or to process a user-generated traffic map. Applications would be to have a traffic situation map on the internet, having traffic messages or including traffic messages saying where are congestions and major delays inside the traffic network, and as well level of service measurements, so which are significant travel times on several way segments, as well as tailback lengths or average waiting times and travel speeds. So I brought two nice examples today, significating which GNS data communities or portals are already existing, using individual GNS data for processing a traffic model. And one major company is TOMTOM with its live traffic. And I mean, there are a lot of advantages because you can see clearly where are major traffic jams or traffic congestions inside the road network. But on the other hand, most of the users did not even know that they are part of this active contribution of data, because you're using your normal navigation device, and TOMTOM is using this data without even knowing, or most people don't even know that they are part of this live traffic. Another way is the community approach, or following a community approach. The project is called WAZE. Maybe some of you heard already about it. It's really nice because it follows, as I already told, the community approach. Users can report minor traffic or major traffic reports, so saying that there are accidents or incidents on the traffic network, as well as congestions, or even if there are speed controls. So to come back to OpenStreetMap, what contribution can the OpenStreetMap project actually do concerning traffic detection? And what we basically did is we were focusing on the OSM GPS data, which is already behind the OSM world map, because users are using this individual GPS data for spatial positioning the roads, and they are using their GPS loggers. Currently there are around 1.9 billion GPS coordinates worldwide, and our task was, or our aim was, to find out whether we could use this data to derive key figures of traffic or level of service measurements. And as you can see over here on the right diagram, the actually amount of GPS log or track data is steadily increasing, and I think now it's August 2010, already 5,000 GPS tracks each month are, so really increasing. And on the left side you can see the JOSM editor with all GPS data we were extracting from the OSM GPS inside at Salzburg. This is just the background of our research we were doing. So it's already starting at 2002, and now we are going to a little bit more in detail, having a look at the pre-analysis of GPS tracks. So as you can see over here, we're just having a few different mode of transports and displaying the data we can derive from. So we have at first the position, of course, then we are having a timestamp, so we are already knowing with which speed one single individual user was moving along the traffic network at a several time. And we can also calculate other measurements like acceleration, of course, the speed, and also the heading change rate, so detecting drifts. And this is really a significant value, because we were using this drift to detect or to implement a mode of transport recognition, because we don't actually know how the user moved along inside the traffic road network. So was he a cyclist, or was he going by bike, or with a car? And our process was, we just basically extracted all the GPS data, filtering only GPS data which contained timestamps. We then did an error detection, so filtering out increasing or increased speeds which are not real. Afterwards, we will continue with a mode of transport recognition I already mentioned, and at the final part we map matched these GPS tracks on the OSM data, on the OSM network, and finally the output was a traffic map 2.0. So this is just one GPS track also in Salzburg. As you can see on the Z-axis, this is the actual speed the cyclist was moving along on the Salzburg River. And as you can see over here, because of this tunnel, there was this signal interference through the underpass, and we were able to capture these speed or error speed value with our error filter. Afterwards, we were implementing the mode of transport recognition. There are two tasks to do at first, because there are intermodal routes. So the use case would be that a user was using his GPS log and moving as a pedestrian, for instance, and as a and he was going continuing his trip with train or by train. And what we did over here is we were processing the data using a multiple cluster analysis in order to having an output of several potential turning points, so where the user was switching his mode of transport. In this case, we really detected quite well, analyzing the speed and the heading change rate, where there would be a transit point. So in this case, it was a transit point between train and footway. And the output was two clusters, and one was a train and the other one the footway. And afterwards, it's quite easy to map match these data then on the road network or back to the road network. So we extracted the OSM data. We used a routing OSM graph, so just filtering out only the necessary data, leaving out buildings, etc., and only using traffic signals and, of course, the OSM road network. The next goal was to map match all the OSM GPS tracks on the road graph, and the last step we just did traffic analyzing, so determining velocities, tailback lengths, and waiting times. I just put a good example, bring along a good example with me today. This is also inside Salzburg in the Ignaz-Harrer route of Bibelstraße. It's quite a major road going or leading from the German part of to Austria inside Salzburg, the inner city. And this was just one test area we used, because we could really extracted a lot of GPS data on this route, on this race segment. And we at first used or extracted all GNS positions where there was no movement. So on this traffic signal, as you can see over here, and then we determined or calculated the tailback lengths to the original position of the traffic signal. And it's, as you can see over here on the right side on the diagram, it's a good indicator for determining or visualizing the different traffic flow conditions inside the road network. depending on the daily the different day times. So at between 8 and 9 o'clock on this WAZE segment, there was a tailback length of 35 meters. And as you can see, when we were approaching the rush hour times from like 4 to 5, there was already 104 meters, the average tailback length we were calculating from these GPS data. Another really interesting part was building or setting up a standstill grid with a resolution of a 10 per 10 meter grid to see differ between out of town and into town, and determining where are some major traffic congestion points inside the road network, and all the data we used here was also extracted from OSM GPS, and as you can see over here, this was the example I was showing on the sheet before. There's a huge standstill cluster of more than 45 seconds overall GPS data we were extracting from this area. Yeah, when we go on at our level of service, you can see over here, this is also a good example, seeing how the speed values are changing when a single user is moving along inside the traffic network. So we can, from one GPS track, we can clearly identify different speeds and match them to different WAZE segments, and also comparing it to a database with several more GPS tracks, and then detect whether this is a single situation or this might occur steadily over every Monday between 8 and 9 o'clock. So it would be a good indicator. Maybe a last good example is also a roundabout I was visualizing here, and because the OSM users are using GPS loggers, and we are having intermodal routes, so not only cars, and as I mentioned before, also cyclists. And over here I'm going to show a comparison between the level of service of a car movements or car GPS positions and a bus, and as you can see over here, there is a separate bus lane at this roundabout, and having a closer look at the OSM GPS data, you can also see that the traffic congestion, so the traffic density is also smaller. The part of this data, the overall GPS tracks we were extracting there was actually really smaller for buses than for the individual motorized transport. What is the conclusion? I think there's a strong penetration right now of mobile location technologies, and these methods and approaches we developed can be, I think, a really good basis for an upcoming online traffic model. And the historical OSM GPS data we were using really provided a quite good view on evaluating the quality of the transport network. So it's really good for improving the traffic planning. Of course, it is not a real-time traffic model, but this historical OSM GPS database allows clearly to visualize what are some major standstill areas inside a road network. So for traffic planning purposes, this would be a really good way to find out where are the actual problems inside a road network. Yeah, so I'm finally already coming to my end. Thank you.
Thank you very much. Are there any questions for Enrico? Yes. Oh, yeah.
First of all, great work. Seems really interesting. I was wondering about the mode of transport detection. I can see how you distinguish a bike from a car, say, but bus and a tram and a car, they're very similar. Do you try and go somehow by it's 5 meters to the side, so it's a bus lane? That would be very inaccurate in a GPX. Or how do you tell a bus from a car? Like, those are so similar.
Yeah, you're right. This was actually one of the most toughest parts to actually to differ between buses and cars inside the traffic road network. So we didn't use any localization with the OSM road network in the background. We just were focusing about the values, so the heading change rates, the speed, and the acceleration, and between the other mode of transports, we could clearly recognize or differ between the mode of transports, but between cars and buses, you're right, this was the one issue we couldn't solve when using this mode of transport recognition. But with the other GNS positions, for instance, like the train positions or buses going a little bit more faster, like on the outskirts, we could clearly see the still stand sequences of bus positions having the approaching to a station, and when we used this cluster, then we could clearly see, differ between those different mode of transports.
How difficult is it to track the GPS data to the actual network, the recorded tracks to the...
So you were focusing on the map matching process. Oh, yeah, all right. We were following an approach using probabilities. So we were matching each single track on the OSM network, and our method was calculating at first each single point, the probability of being a part of this WAZE segment, and in the end it was calculating a total probability, which route might be the route with the most probability. The GNS track position was, or the user was moving along with this GPS logger, and the accuracy was around 90%. So the most toughest part, or one major problem, was map matching cyclist or pedestrian data, because then the speeds are really decreasing or really low, like 5 kilometers on average for 5 kilometers per hour, and the GPS signal was really drifting on the network. So this was a quite major problem to map match these data. But for traffic analyzing purposes, we didn't use the cyclist or the